When the statement emerged from Beijing, it was unlike routine scientific releases. China's latest assessment of the interstellar object 3 Atlas was brief, technical, and direct in its findings. Rather than announcing fresh detections, it served to validate earlier interpretations. The report stated with strong confidence that 3 Atlas was an interstellar body, defined by a hyperbolic path and an unusual chemical makeup dominated by carbon dioxide. Within the carefully translated summaries, one line stood out. Nothing about the object has changed, and yet everything has. For a document of this kind, the phrasing was striking, restrained yet contemplative, implying that while the data itself was unchanged, its significance for astronomy had come sharply into focus. For months, astronomers worldwide had followed a peculiar visitor passing through the solar system, an icy, fast-moving object that did not belong here. At first it was a novelty, then it became an obsession. By the time China's findings reached the global scientific community, 3I Atlas was no longer merely another interstellar comet. It had become a reflection of both the limits of human observation and a shifting balance of scientific influence on Earth. On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System, known as ATLAS, detected a faint moving point of light using its telescope network in Chile. Initially, analysts assumed it was an ordinary comet, but its motion refused to conform. Within days, orbital calculations confirmed it was not gravitationally bound to the Sun. Its trajectory was open, hyperbolic. It had arrived from beyond the solar system, would pass through once, and then vanish forever. The object was officially designated 3I Atlas, the third interstellar visitor ever recorded, following the enigmatic Oumuamua in 2017 and Boros in 2019. Each of these rare arrivals appeared without warning, racing through the solar system at extraordinary speeds. To scientists, they were invaluable frozen envoys, carrying chemical signatures from distant stars. Yet unlike the others, 3I Atlas appeared at a moment when human systems faltered. Its arrival would reveal how fragile our supposedly global watch of the sky truly was. At first, events progressed smoothly. Telescopes in both hemispheres fixed their gaze on the newcomer. Hubble captured optical images. The James Webb Space Telescope, positioned far beyond Earth's atmosphere, examined it in infrared. Ground-based observatories from Hawaii to the Canary Islands joined the effort, tracking changes in brightness. Early calculations placed its heliocentric velocity at more than 209,000 km/h. The object followed a steep course through the inner solar system, plunging toward the sun's glare before being flung outward again toward the stars. As weeks passed, the data began to reveal oddities. Most comets brighten as water ice sublimates when nearing the sun. This one did not. Spectral analysis showed its coma, the diffuse cloud surrounding the nucleus, was not driven by water. Instead, carbon dioxide, CO2, glowed faintly in the vacuum. Water, the usual engine of cometary activity in our solar system, was nearly absent. That single detail suggested 3 Atlas had formed in a radically different environment, perhaps in the frozen outskirts of another stellar system. Then, just as the comet entered its most revealing phase, its closest pass to the sun, Earth blinked. In late September, for 36 hours, almost every major Western observatory went offline. Hubble paused for a scheduled gyroscope realignment. The James Webb Space Telescope began a planned instrument switch, a process requiring more than a day of thermal stabilization. In Chile, the Very Large Telescope entered maintenance, its massive mirrors undergoing cleaning. Gemini North and South shifted to pre-approved planetary programs. Each decision made sense on its own, but together they produced something rare, a global blind spot. The timing could not have been worse. During that precise window, 3I Atlas crossed a region of sky dangerously close to the sun's glare. From Earth, observation became nearly impossible without specialized systems. With each unobserved hour, scientists risked losing vital information about outgassing rates, coma evolution, and chemical composition. To the public, the pause went unnoticed. To astronomers, it was catastrophic. A gap in the light curve of an object that would never return. Except the sky was not silent everywhere. Across the Pacific, China's high-altitude observatories in Tibet, Qinghai, and Yunnan continued watching. Their schedules, independent of Western institutions, left them operational during the blackout. The clear, dry air at these sites, thinner and colder than most locations on Earth, enabled continuous optical and infrared observation. While the world's largest telescopes paused for recalibration, a network of smaller instruments atop Asia's roof captured the only uninterrupted data stream of the interstellar visitor. Each observatory followed a rigorous procedure. Light gathered by primary mirrors was focused onto cooled CCD sensors, with exposures lasting between 30 and 120 seconds. At the comet's extreme speed, longer exposures risked motion blur. Every image was time-stamped to within a millisecond using GPS clocks and saved in standardized FITS format, preserving not only the image but metadata including coordinates, filters, temperatures, and environmental conditions. These files were sent via fiber optic links to centralized servers in Nanjing and Beijing, where redundancy systems kept them running despite sub-zero temperatures. Engineers referred to them as servers under ice. By the time Hubble and JWST returned to operation, 3IE Atlas had already traveled more than 1,000,000 km along its trajectory. Without the Chinese observations, scientists would have faced positional uncertainties so severe that reacquiring the comet might have required blind searches. Instead, China's data allowed the global network to realign. The mountain observatories had closed the gap with remarkable precision, delivering continuous measurements of brightness and position that restored the global timeline. The findings were striking. During the 36-hour blackout, 3E Atlas brightened by roughly a third of a magnitude, a modest rise but sufficient to signal increased activity. Its coma stretched toward the sun, indicating a jet of gas and dust erupting from the nucleus. Subsequent analysis revealed the dust grains were unusually large and carbon-rich, a combination seldom seen in comets formed within our solar system. As the data spread, it became clear that something significant had taken place, not only in astronomy, but in geopolitics. For decades, the world's premier observatories, funded by Western consortia, had defined the limits of astronomical knowledge. Now, for the first time, the most crucial observations of a historic interstellar event originated elsewhere. The instruments that proved decisive were not the largest or most expensive. They were simply the ones that remained active. Still, questions of trust remained. Integrating Chinese data with Western datasets required meticulous calibration. Variations in software, wavelength alignment, and photometric scales had to be resolved. Chinese researchers documented every step. Brightness was calibrated using Landault standard stars, magnitudes cross-checked with the Sloan Digital Sky Survey, and spectral lines corrected with thorium and neon lamps. Independent teams in Hong Kong and Taiwan verified the results within narrow error margins. Once merged, the global dataset achieved unprecedented precision, astrometric accuracy within 1/5 of an arcsecond, eccentricity fixed at 1.19. The conclusion was undeniable. 3 Atlas was interstellar. Beyond the figures, the episode exposed an uncomfortable reality about modern astronomy. Despite its rhetoric of international collaboration, the system remains uneven. Of the world's 30 largest telescopes, those with mirrors exceeding 6M, 2/3 are based in the Americas or run by Western partnerships. China's telescopes are smaller, generally between 2 and 4M, but their advantage lies in automation and distribution. Multiple mid-size instruments operating together can outperform a single giant when timing and coordination outweigh raw sensitivity. Large telescopes are built for depth, to probe faint galaxies billions of light years away. Smaller observatories excel at continuity, monitoring the same region of sky hour after hour. For fast-moving or transient targets like 3 Atlas, that persistence can matter more than aperture. During the blackout, China's robotic scheduling software reassigned telescopes in real time as weather and target geometry changed. By stacking hundreds of short exposures and statistically combining them, the network achieved a signal-to-noise ratio comparable to much larger Western instruments. Persistence, not size, became decisive. Symbolically, it was about access. Who has the ability to see and record the universe? For decades, the largest mirrors represented prestige and control. The 3 Atlas campaign reversed that equation. The most complete record of a cosmic event did not come from the biggest telescopes, but from those willing and able to keep observing while others paused. When the final combined analysis was released, the wording was cautious yet clear. The data confirmed that 3I Atlas consisted mainly of carbon dioxide ice, that it originated beyond the solar system, and that it passed through only once before returning to interstellar space. But beneath those conclusions lay something more, an acknowledgement that this discovery marked a shift. For decades, Western science had been the unquestioned guardian of cosmic truth. Now observation was truly global, and the balance of its links had changed. The implications of that shift extended far beyond a single comet or a single observing window. In quiet discussions following the release of the combined analysis, astronomers began to acknowledge what the data itself could not say outright. 3 Atlas had not only tested theories of interstellar chemistry and dynamics, it had tested the structure of modern science. For decades, discovery had followed a familiar hierarchy. Detection flowed upward from regional surveys to flagship observatories, then outward through peer review to the world. This time, the flow bent sideways. Continuity, not hierarchy, determined authority. 3 Atlas itself continued on its relentless path, indifferent to the debates unfolding beneath it. As it receded from the inner solar system, its brightness steadily faded, its coma thinning as solar radiation weakened. Within weeks, even the most sensitive instruments struggled to track it. Eventually, it slipped beyond detection entirely, becoming once again just another fragment of interstellar debris drifting between the stars. But the data it left behind remained dense with meaning. The unusually high carbon dioxide content challenged prevailing assumptions about comet formation, suggesting that planetary systems elsewhere may favor radically different volatile chemistries. The large, carbon-rich dust grains hinted at slower aggregation processes or colder formation zones than those typical of our own solar system's early history. The event also forced a reconsideration of preparedness. Interstellar visitors do not announce themselves. They arrive on hyperbolic paths, moving faster than most survey systems are designed to prioritize. 3 Atlas had been detected only months before perihelion, leaving little margin for error. The 36-hour blackout demonstrated how fragile even the most advanced monitoring network could be. Modern astronomy relies on precision scheduling, long-term proposals, and carefully optimized use of scarce resources. That efficiency, however, comes at the cost of flexibility. When every minute is allocated, there is little room for the unexpected. Quietly, observatory directors and mission planners began re-evaluating those assumptions. Discussions emerged about dedicated rapid response networks, autonomous systems designed to override pre-planned schedules when transient events appeared. The Chinese model, once viewed as supplementary, now looked prescient. Distributed telescopes, coordinated by software rather than committees, had proven capable of filling gaps no single flagship instrument could. The lesson was uncomfortable but clear. Redundancy was not waste. It was resilience. Politically, the episode lingered in subtler ways. Scientific influence has always been tied to infrastructure, and infrastructure reflects national priorities. For years, Western dominance in astronomy had rested on sheer scale. Larger mirrors, deeper surveys, farther reach. 3 Atlas showed that reach alone was not enough. Timing, latitude, and autonomy mattered just as much. Access to clear skies during a narrow window had outweighed decades of investment elsewhere. It was a reminder that the universe does not align itself with funding cycles or institutional prestige. Among younger scientists, the reaction was different. To them, the event felt less like a loss of dominance and more like a correction. Astronomy, they argued, had always claimed to be global. Now it finally was. Data from Tibet, Qinghai, and Yunnan sat alongside measurements from Hubble and JWST, indistinguishable once calibrated, equal in weight once verified. The sky had not changed, but who could speak for it had? In the end, 3E Atlas left no artifact behind, no sample to analyze, no mission to plan. Its legacy was intangible but enduring. It exposed blind spots, both literal and institutional. It reminded humanity that the cosmos does not wait, and that discovery favors those who remain vigilant when others pause. Long after the comet vanished into the dark, that lesson continued to resonate, quietly reshaping how the next visitor from another star might be seen, understood, and remembered.